Hey everyone, I'm Jessica from Aspyre, and today I'll be taking you guys through part 5 of our Algebra and Functions unit, Exponential Functions. Today's math quote of the day is from Pythagoras, an ancient Greek philosopher who's most famous for a theorem under his name, the Pythagorean theorem for right triangles. Pythagoras says, "There is geometry in the humming of the strings. There is music in the spacing of the spheres." So first off, what is an exponential function? The definition of an exponential function is a function that can be expressed in terms of a to the power of x, where a is greater than 0 and not equal to 1, and x is any real number. We call a the base and x the exponent of the function. At the right, we have f of x equals 2 to the power of x, which is an example of an exponential function. The x values on the left column make up part of the function's domain, a concept we learned about in part 1, and the y values make up part of the range. Next, let's look at some properties of exponents. Below we have the law of exponents, which consists of several rules. First, let a and b be non-zero constants and mn be any real number. For the product rule, we can say that the product of a to the power of m and a to the power of n is equal to a to the power of m plus n. For the power of a product rule, we can say that ab to the power of m, where ab signifies the product of a and b, is equal to the product of a to the power of m and b to the power of m. Next, for the quotient rule, we can say that the quotient when a to the power of m is divided by a to the power of n is equal to a to the power of m minus n. Next, for the power rule, we can say that a to the power of m to the power of n is equal to a to the power of mn, or the product of m and n. Finally, for the power of a fraction rule, we can say that a over b to the power of m is equal to a to the power of m over b to the power of m. And we have to make sure that b is non-zero because dividing by 0 leads to an undefined result. And something we can notice here is that for the product rule, we're adding the exponents, whereas for the quotient rule, we're subtracting the exponents. And on the right, we have more rules for 0 and negative exponents. Let a be non-zero and m be a positive number. For the 0 exponent, we can say that a to the power of 0 is equal to 1. So 1 to the power of 0 is 1, 2 to the power of 0 is 1, 3 to the power of 0 is 1, and so on. For the negative exponent, we can say that a to the power of negative m is equal to the reciprocal of a to the power of m, or 1 over a to the power of m. Note that we keep the base the same when using these rules. Now let's apply what we've learned so far to answer a few questions. For example 1, if x equals 2 to the power of a, try expressing 2 to the power of 2a plus 1 in terms of x. Using the product rule in reverse, we know that if the exponent is a sum of two values, in this case 2a and 1, we can rewrite this expression as a product of 2 to the power of 2a and 2 to the power of 1, or 2. Next, using the power of a product rule in reverse, since the exponent is a product of two values, 2 and a, we can rewrite the expression into 2 to the power of a to the power of 2 times 2. 2 to the power of a to the power of 2 is equal to 2 to the power of 2a. And this will be equal to 2x squared when we substitute x equals 2 to the power of a. For the second example, we know that 3 to the power of x plus 3 to the power of x plus 3 to the power of x is equal to 3 times 3 to the power of x. Using the product rule like we did for example 1, we can say that's equal to 3 to the power of x plus 1. And if two exponential expressions have the same base and are equal to each other, then their exponents must have the same value as well. Here the base for both expressions is 3, and the expressions are equal to each other. Then we can say that x plus 1 is equal to 2x minus 1, and this turns into a simple algebra problem that yields the answer of x equals 2. Finally, we have compound interest, which tells you how much money you'll have to return to a bank depending on the initial value of your loan and the interest rate. Compound interest concepts can also be applied in various other contexts. including investment, population growth and decay, bacteria multiplication, and more. So let's define a few variables. A is equal to the final amount. P denotes the principal amount, or the initial investment. R signifies the annual interest rate. T signifies the number of time periods, which when calculating compound interest is usually 1 year. And N denotes the number of times interest is applied per time period or per year. So the final amount, when interest is compounded n times per year, will be equal to P, or our initial value, times 1 plus R over N to the power of N times T. When interest is compounded once a year, then we know that N would be equal to 1. So the formula would be A equals P times 1 plus R over 1, or R, to the power of 1 times T, or T. And when interest is compounded continuously, the variable N, or the number of times interest is compounded per time period, doesn't have a specific value. Therefore, we have a new formula to express the final amount, which will be equal to P times E to the power of RT, where E is Euler's number. We also included the formula for simple interest for reference, where P is the principal amount or initial amount, R is the interest rate, and T is the number of time periods or years. The final amount equals P times 1 plus RT. Since simple interest is not compounded, it is not an exponential function. Thank you all for watching, and we hope this helped. Next class, we'll be moving on to our final part, part 6, which will be about logarithmic functions. Goodbye.